This question reads, two forces with magnitudes 5 newtons and 12 newtons act from the same point on an object. Calculate the magnitude of the resultant force R for the forces acting in opposite directions and at right angles to each other. So in opposite directions, you could say there's a tug of war with 12 newtons acting thisly and 5 newtons acting thusly. And therefore there will be 7 net newtons acting thisly. Right, and so that should be pretty clear. We use a sign convention. If this is positive to the right, that's negative to the left, right? Opposing it. And so we, add those two vectors, or we add the negative, and so it's 7 newtons, to the right. So that's sort of plus 7. Now it just wants the magnitude. So our sign convention is just a way to keep track of this opposes that. The magnitude, though, is just saying, well, what's the how much, right? So it's a force vector, right? Force is a vector. We don't really care about the direction if they ask us for the magnitude. Now, if they're at right angles to each other, that's a little bit tougher of a calculation, right? So we have a 12 Newton force this way, and they're acting on the same point, but remember, that just means we're summing these vectors. And the way that we sum vectors is to put them head to tail, right? And so let's say we had our 12 Newton force acting this way and our 5 Newton force acting, to the right, but it's at the same point. It's acting on this object, but to add them, we're going to sort of draw them like this. And then we know that the net force would go this way, but we don't really care about the direction, right? It just says calculate the magnitude. They don't really tell us anyway. They just say at right angles. We could have drawn this triangle any number of ways. Like, if this way is north, then this could point, to the east or the west, whatever, as long as it's a right angle. So you should recognize by now that Pythagoras' theorem is the helpful one to solve this, right? So 12 squared plus 5 squared equals, we'll call this R. For the resultant squared. 144 plus 25 equals this squared, and that's 169. And I think that's 13 even, right? That's a perfect square. Square to 169 is 13. 169. Yeah, 13. We got 13 newtons going that way. Now we could calculate the angle if we needed to, if they asked us for like, what is the vector, right? Which would be the magnitude and the direction. That's just a quick reminder. If we needed to calculate, say, this angle theta, then the inverse tangent of 5/12 would solve that, right? The inverse tangent of opposite over it solves for the angle. It looks like now we've got object X rests on a smooth horizontal surface. Two horizontal forces act on X as shown in figure 1.1. Okay. It says it's not to scale also. So they've drawn this one, this long, this long, but this is 55, this is 18. So we could represent the magnitude of these vectors by drawing sort of a scale diagram, but this one is not to scale, so that's not helpful. A force of 55 newtons is applied to the right. Got it. A force of 18 newtons is applied at an angle of 115 newtons to the direction of the 55 newton force. So here's the object that's being sort of pushed to the right and pushed down like this. So both of those forces are acting on point X like this. But if we wanted to add them, remember we put them, well, I guess they are, right? It says use the resolution of forces or a scale diagram to show that the magnitude of the resultant force acting on X is 65 newtons. So here it's saying we could either solve this with a scale diagram or we can solve it with resolution of forces. So we'll do it the resolution of forces way, but we could get, a ruler and, say, well, I'll just draw one 1.8 centimeters, draw one 5.5 centimeters, use my protractor to get that angle right, and then actually just measure the length of the resultant. And on that scale, where this 1.8 centimeters is an 18 Newton force, just multiply it by 10 and centimeters or newtons. But we'll use resolution of forces. So this vector here is the one that's tricky because this one is directly to the right. And if this one goes down and to the right, then let's just think about it as it's got a component that goes down and it's got a component that goes to the right. Now this is always tricky here, figuring out all these angles, right? So we got 115 degrees this way. There's our 90-degree angle right there. So we can figure out this angle. Easy enough, right? It's the supplementary angle to this 115-degree angle. So if we take 180 minus 115, that gives us 65 degrees here. And then we know that's 90, and so this hypotenuse is the 18 newtons, right? Like that's the vector that we're resolving into down and right components. So now I think we know enough about this triangle to figure out the down and the right components. We'll use the 65-degree angle, and we'll say, well, this side is opposite. So the sine of 65 degrees, the function of the angle relates the opposite to the hypotenuse for the sine, right? The so and SOHCAHTOA. So sine of 65 equals the side opposite. Let's just call this the force vertical. Okay, so it equals the vertical component of this 18 newton force divided by the hypotenuse, which is the 18 newtons. So the vertical component of that force is going to be equal to 18 newtons times sine 65 degrees. Sine of 65 is 0.906 times 18. So we get the down component 16.3. So the over component here is going to be adjacent to this 65-degree angle. And so the helpful function there, I'll write it up here. In fact, I'll just redraw this triangle like this. So we know there's our 65-degree angle. We want to know this side. I'll call it the horizontal component of force. 18 newtons is the force up here. And so now we can write the cosine of 65 equal to adjacent over hypotenuse. Multiply those sides by 18 newtons, and we solve that the horizontal component is 18 newtons times cosine 65. Cosine 65.422 times 18, 7.6. Now, we want the total force, right? We were asked to solve for the net force using resolution of forces. Let's show that the magnitude of the resultant force acting on X is 65. So let's back up here. So X is this point, and we've got a force of 55 newtons acting on it this way. And we've got a force of 7.6 newtons also acting on it this way, right? That to the right force makes it even more this way. But then we got a down of 16.3 newtons. So our net force will be this, right? So it kind of goes this way. And what's it going to be? Well, it's going to be 55 newtons plus 7.6, 62.6 to the right, 16.3 down. And so we should be able to solve this again using Pythagoras' theorem. That's the hypotenuse. There's our right angle. This is to the right. This is straight down. So again, the point of resolving a vector is to figure out how much in the x, how much in the y. We resolve the vector that isn't perfectly aligned with the x and y axes to figure out how much of it is aligned sort of in each dimension. And so now we've got 62.6 squared plus 16.3 squared, a squared, right? That length plus b squared, that length equals, we'll call it r for the result. Let's be creative. Yeah. 62.6 squared plus 16.3 squared equals 4,185. We need the square root of that. And we solve that this R equals 64.69, which is indeed about 65 newtons, which is what they asked us to show. So that's how to do it with resolution of forces. It says use resolution of forces or a scale diagram to show. And so resolution of forces, we resolve the 18 Newton vector and x and y components, add them back in. Our 55 Newton vector, still going to the right, so don't forget about that. So there's the sum Pythagoras' way. Let me go ahead and show you the scale diagram method now. You draw your 55 Newton vector like that. You use your protractor to realize there's 118 degrees coming in like this, and so it's going to kind of go like that, but only 18 compared to this 55. So there you draw this and you measure it, and as you measure it, you go, oh yeah, on my scale that works out, 65 newtons. Check, there you go. You got to actually use a ruler, use the protractor, right? We showed it the resolution of forces way. On-screen ruler for that. Determine the angle between the resultant force and the 55 Newton force. So we want, I guess, this angle right here then. It's saying the angle between the resultant force, well, that's that one, and the 55 Newton force, that was the due right force. So this angle here, I think we'll just use, again, opposite, adjacent, we know them. So we can say that the tangent of that angle theta is equal to opposite, 16.3, over adjacent, 62.6. And so the angle theta then would be the inverse tangent of that ratio of sides. (16.3 over 62.6, 0.26), and the inverse tangent of that is 14.6 degrees. Hmm. 14.6 degrees would be the angle there. Again, just sort of keeping in mind that we had our 62.6 this way, and that's the same direction as the 55 Newton force. We had our 16.3 down, and so we're really just solving for this angle right there. And again, the inverse tangent of that ratio of sides solves for the angle. You get 14.59 and so on. So you could round that to 14.6. If you want to keep 3 significant digits, we'll take a look at the mark scheme. Maybe they just have this as 15 degrees there. We'll see what the mark scheme says in just a moment. It says a third force of 80 newtons is now applied to X in the opposite direction to the resultant force in B. So it's like, here's the resultant force in B. Remember, it was about 65 newtons. Now we're just going to play tug of war this way, go the exact opposite way, 80 newtons like that. The mass of X is 2.7 kilograms. Okay, so we got a mass here, 2.7 kilos. All right. Calculate the magnitude of the acceleration of X. All right. I think everybody's ready for this. I think everybody's like, okay, this question really geared us up to answer this thing. It had to start with, let's not get too far back there, everybody. This question had to start with what? Just a little bit of vector addition, opposite directions. Oh, bingo, right? If you knew how to do this, if that made sense to you to go 12 minus 5 gave us 7 up here, right? We know how to add forces that oppose each other. It's exactly the situation we're dealing with down here now. You see how the question is really setting you up to prepare you for this ultimate calculation. It took a lot of work to realize, prove this was 65. But even if you couldn't get that, it told you, right, this was the net force, 65, show that it's this. Now we know that we have an 80 Newton force opposing. So we know what the net force is going to be. Think about the sum of the forces equals mass times acceleration. Newton's second law of motion. We've got something with a constant mass, right? They had to give us that mass for a reason. And we're solving for the acceleration. So we just got to get the net force now. So it's going to be 80 minus 65, right? Because they're opposing each other. So 80 minus 65 gives us a 15 Newton force. equals 2.7 kilograms times acceleration. Divide each side by 2.7 kilos. This was our answer for the angle, right up there, remember? So 15 divided by 2.7 gives 5.6 meters per second squared. Thanks for tuning in. This has been another worked example with Dr. Schleif. We'll see you next time.